All right, good morning, ladies. So, just to remind you what we were talking about. So again, we looked at the magnetic field from a straight wire. So again, what we said is that that falls off as 1 over r. So if we plotted the magnetic field, it would reduce as you go further and further away as 1 over r, which then led us to look at the force between now 2 parallel wires. So again, what we said was that if the currents were in the same direction, that resulted in an attractive force. And if they were in, pardon me, if they were in opposite directions, then that's resulted in a repulsive force. So basically to show that, I brought this wonderful contraption. So basically here, what this is it creates a circuit. So right now I have it set up in parallel. So what it'll do is it'll run a current. That current will then go through these 2 rods, which are then constituting as a wire. So here, since it's in parallel, the 2 currents will be in the same direction. So hopefully you can see this. Thanks to my kids writing all over the board. But anyways, if I hit this button here, it'll run the current. And in this case, you can see the 2 wires are actually attracted to each other. Right? So hopefully you can see that on here. So again, if I separate them, run the current through them. In this case, you can see the 2 wires being attracted. There we go. Now, if I unhook this, I'm going to put them into series. So if I unhook this guy, run this guy now through here. So this will put this into series. So now if I put them close to each other and do the same thing, so now they go apart because now they're running in opposite directions, which now results itself in a repulsive force. And I just broke it, so that's so anyways, so that's kind of a demonstration of that effect that we're seeing here. So again, just kind of remind us of this effect. So again, force between 2 parallel wires, as long as these guys are parallel to each other. In this case, we have the force is then mu naught times the current through the first wire times the current through the second wire times the length, where the length is then the length of the wire itself. Divided by 2 pi times the distance between the 2. And again, if they're in the same direction, that is an attractive force. And if they're in opposite directions, then that is a repulsive force. So we've done one example, but let's do another example. So this example says that we have these 4 wires, which are then in a configuration of a square, where the 2 wires on the left have current running out, so the current is running towards us, and then the 2 wires on the right here are running in. And they're each carrying a current which is identically the same, so it's 7.5 amps. The distance between the wires here, A, is 13.5 centimeters. And what we want to know is on this bottom wire here, which is what I'm calling the 4th one, what then is the net force on this guy? Okay. So just for notation's sake, I'm calling the upper left-hand corner here I1. So, oops, let me go back to here. So I'm calling this guy I1, calling the upper right-hand corner I2, lower right-hand corner I3, and then the lower left-hand corner I4. So we're looking for the net force on the 4th wire here. Right? Where again, these 2 are coming out, these 2 are going in. They all have the same amount of currents of 7.5. So let's redraw our scenario. So let's say here is 1 wire, 2 wires, 3 wires, and 4 wires. And these ones are coming out with our currents. So I'm going to call this I1 and this one I4. This current is going in. This one's also going in. So I'm going to call this one I2 and this one I3. And again, we want to know is what is the force on this guy? So what is the force on wire 4 here? Good. So this is what we want to know. Now, again, we know that all the currents are the same. So we're going to write I1 is equal to I2, which is equal to I3, which is equal to I4, which is equal to 7.5 amps. And we know that each one of these guys is a distance A away from each other. So this is A and A, where A is 13.5 centimeters, if I remember correctly. Yes, good. So good. So since this is the force, what that means then is the same thing as before, which the force on wire 4 is simply then going to be equal to the sum of all the individual pairs. So this is going to be the force on wire 4 by all of the other wires, which means this is going to be the force on wire 4 by the first wire, plus the force on wire 4 by the second wire, plus the force on wire 4 by the third wire, written in vector form. So here we're going to eventually write this as a magnitude and an angle, but here we're just going to write this as vector components. So here we're going to use the fact that, let's choose a coordinate system. So let's say my y direction is upward, my x direction here is to the right. I actually knew how to draw, there we go. So here we're going to use the same thing that we did before, which is when we did charges and electric fields, what we know is that here, if I have currents which are running in the same direction, that has to be a attractive force. So that means is that the force on wire 4 by wire 1 will be pulling it towards wire 1, which means the force on 4 by 1 will then be upward toward wire 1, because that is an attractive force. Wires 2 and 4 are opposite in direction, which means that that is going to result in itself in a repulsive force. So in this case, I'm going to have a repulsive force in this direction. So this is then going to be F42. And then finally, 4 and 3 are also running in opposite directions, which means that's also going to be a repulsive force, which means that F43 is going to be along the negative x direction. So that tells us then, if we vector sum all these together, our total force then should point somewhere off in this direction, right? So this is going to be F4. So the vector force sum between all those is going to be somewhere off in this direction, which tells us then that our answer should be somewhere in the second quadrant. So somewhere between 90 and 180 degrees. So good. So good. So basically, as we did before, since this is a two-dimensional problem, what we're going to do then is look at the x component of the net force and look at the y component of the net force, and then use Pythagorean theorem then to determine the magnitude of all of that. So we're going to look at the x component of that force, and also look at the y components of the force on on wire 4. Good. So first off, what we can see then is F41 only points along the y direction, which means all of that force is along the y direction and points in the positive y direction. So this is going to be simply F41 in the y direction. We see that F43 points in the negative x direction, only in the negative x direction. So I'm going to write a minus F43 here. And then F42 then points off in both the x and y directions. So this angle here, since this is a square, what that means is that this is an angle of 45 degrees, which means this is also an angle of 45 degrees. So here, this is in the negative x direction. So it's going to be minus F42 times cosine of 45 degrees. And then here, I'm going to get a negative F42 times sine of 45 degrees, because again, that's in the negative y direction. Okay. So now we're going to go back and use the fact that the force, again, is equal to mu naught. So the force Fi is then going to be mu naught I4 times II. So this is whatever that I is going to be, times the length. Now here we're looking for actually the force per unit length. So we're going to divide by that length and just call it a day, divided by 2 times pi times the distance di. So it's the distance from that wire to the fourth wire. So let's use that here. So first of all, they all have a mu naught, so we can factor that out. They're all going to have a pi or I4, so we can factor that out. And they're all going to have an L, so we can factor that out as well. So I'm going to write this as minus mu naught I4 times L divided by 2 pi, because that's constant on each one as well. Then times, so here this is current I3 divided by the distance, let's call that D3, where that distance D3 is this distance here. So that's just equal to A. Plus this current, so this is I2 times then cosine of 45 degrees divided by that distance. So I'm going to call that D2. We'll talk about what D2 is here in a second. So this distance here is D2. And let's look at the y direction as well. So it's going to be equal to mu naught times I4 times L divided by 2 pi again. So this is now going to be I1 divided by the distance d1, where again d1 is just going to be equal to a minus I2 times sine of 45 degrees, all divided by the distance d2. So from our diagram, we can then see again that d3 is simply equal to a, d1 is equal to a, and then d2, since this is a, what? Right triangle, we can then use Pythagorean Theorem to say that what? d2 is equal to the square root of a squared plus a squared, which is equal to the square root of 2 times a. Everyone's okay with that? So this is our d2. So plug everything in. So this becomes minus mu naught I4 times L divided by 2 pi times A, because they all now have A as a factor, so I'm going to pull that out as well. So this becomes times I3 plus I2 divided by the square root of 2 times cosine of 45 degrees. And then this is going to become mu naught I4 times L divided by 2 pi A times then I1 minus I2 divided by the square root of 2 times sine, of 45 degrees. Okay? Now we go a little bit further. What we also know is that cosine of 45 degrees is equal to sine of 45 degrees, which is equal to the square root of 2 over 2. So actually what's going to happen is those square roots of 2's are going to cancel, and that's going to be replaced by a 2. And we also know that I1 is equal to I2. So finally, we can write this as minus mu naught I squared, because I2 and I3 and I4 are all the same. So I'm going to pull that out, times L, divided by 2 pi A times 1 plus a half. Is okay with that? This one then is going to become mu naught I squared times L divided by 2 pi A times 1 minus a half. Okay. Everyone's okay? Now that I wrote everywhere on that page, I know how many place outs to write, so let's move to another page. So this finally says then that's what? The x component is then equal to mu naught I squared. I'm going to write over L, because I want to divide both sides by L, because I want the force per unit length, times then 2 pi A times simply 3 halves. Okay. And then F for Y over L is then equal to mu naught I squared divided by 2 pi A times a half. Everybody's okay? So finally, we can then say the magnitude of F4 is going to be the square root then of, well, force per unit length, we'll do it that way, is going to be force for x over length squared plus F for y divided by the length quantity squared. So this is the force per unit length. Now, I'm mostly doing that, and I'm factoring all this out because now this factor here is the same as this factor here, so they both have that in common. So when I square it, they both have the same, and I pull it out and just get the square root of that, which is just that same factor. So it's going to be the same thing then as mu naught I squared divided by 2 pi A times then the square root of 3 halves quantity squared plus 1 half or 1/4. It's okay. So now, of course, this is going to be 1/4. With 1/4, I can pull that out. That's going to be 1/2. So it's going to be the same thing as 9 plus 1, which is the square root of 10, right? So finally, this becomes mu naught I squared divided by 2 pi a times the square root of 10 divided by 2. So this is my magnitude. Okay, so let's look at our numbers. So this becomes 4 times pi times 10 to the minus 7, because that's mu naught, times I, which was 7.5 amps quantity squared, divided by 2 times pi times a, which is 0.135, all times the square root of 10 divided by 2. Multiply everything else. What I finally find then is that this works out to be 1.32 times 10 to the minus 4. 1.32 times 10 to the minus 4 newtons per meter. That's okay. The angle is then going to be what? The inverse tangent of the y component of F4 divided by the x component of F4. So now, when I put that in, what I can see then is that what? This prefactor of mu naught I squared divided by 2 pi a is the same, so when I divide one by the other one, that's simply going to go away. So now when I take this guy and divide by this guy, I'm sorry, over L. There we go. Okay. So now when I take this and divide by this term is the same as this term, so they're simply going to cancel. Which means that this is the same thing then as the inverse tangent of 3/2 divided by 1/2. But 3/2 divided by 1/2 is the same thing as simply 3. So this is the inverse tangent of, sorry, one of these is negative. Actually, the x portion is negative. Oh, I did that upside down, didn't I? I did. Sorry, I wrote that upside down. I divided x by y. I wanted the other side. So I want 1/3 or 1/2 divided by 3/2. There you go. So this is the inverse tangent then of negative 1/3. The negative sign comes in. Sorry, I didn't carry that over from the other page. Remember the x portion was negative. So I forgot to carry that over. So this is actually negative. Doesn't change anything we did here because when you square it, that makes that negative sign go away, but that's technically negative. Sorry about that. So this is the inverse tangent then of negative 1/3, which works out to be 161. That's 161.5 degrees. So this is the angle. This is my angle of theta 4. So again, this matches our picture. What we said before was that what our angle should be somewhere in the second quadrant, somewhere between 90 degrees and 180 degrees. And what we find is that this works out to be 161.5, which is somewhere between 90 and 180 degrees. So, is everyone okay with that? I know I went through that a little bit quickly, but so far so good? So far so good. Okay. Good. So that brings us to our first group assignment of the day. So that says that we have a long straight wire carries a current of I1 equals to 30 amps and a rectangular loop with sides 30 centimeters and 8 centimeters. So this is 30 centimeters across here and then 8 centimeters down this way. Carries a current of 20 amps, which is going in the clockwise direction. And these two are separated by a distance of 1 centimeter. So that's what A is here. So here's my long straight wire carrying a current of I1, which again is 30 amps. 1 centimeter below that is the closest side of the rectangular loop, where this is 20 centimeters, 8, 20, 8, and that's carrying in the clockwise direction a current of 20 amps. So Even though it says unit vector notation, don't worry about that. What we want to know is what is the net force on the loop due to this current running in here. So, good. So let's talk about this just a little bit. So basically, what you can think of is that what? This is actually two straight wires, right? Even though here, these guys are connected by these perpendicular wires, it turns out that even though there is going to be a force here and a force here, those two forces are going to be equal and opposite at every location, and those guys are actually going to cancel each other. Which makes this one actually a little bit more difficult, which we didn't actually talk about, is because here we know that this magnetic field from this wire falls off as 1 over r. What actually happens is that at every location along this wire, the force is actually different because it's in a non-uniform magnetic field. So technically, if I wanted to know the force that was in this portion of the wire here, or in this portion of the wire here, we would actually have to integrate because the magnetic field is non-uniform. So it's in a non-constant magnetic field. However, again, what we know is what? In this portion, we know that what? Our right-hand rule says that we put our thumb in the direction of the current, our fingers curl around in the direction of the magnetic field, which means down here, the magnetic field is pointing into the page. Our current is going straight down, so we would point our fingers down, curl towards the magnetic field. Our thumb on this portion would have a force pointing off to the right. Meanwhile, doing the same thing, our thumb over here would be pointing to the left, so this force here would be the same as this force, just in opposite direction. So those pieces would cancel. Which means that the only portions of the force we care about are the force in the upper portion of the wire versus the force on the bottom portion of the wire. Now these guys are in uniform magnetic fields because everywhere along this line, since it's at constant radial distance, has exactly the same magnetic field. And everywhere across here also has the same radial distance, so that also has a constant magnetic field. Now, what's going to be different is the closer you get to this wire, the stronger the magnetic field, which means that what? The force that's going to be on this portion of the wire will be bigger than the force that's on this portion of the wire because the magnetic field here is stronger than the magnetic field here. So what that's going to do is it's going to create a force on this portion which is greater than the force on this portion. Now again, since the magnetic field is pointing into the page, current's running in this direction, curl my fingers in that case, the force on this top part would be upward towards this wire. That's going to be an attractive force, which we can also tell because these two currents are in the same direction, so it's attractive. Down here, this current is running in this direction, so it's going to be repulsive force. But again, this attractive force will be greater than this repulsive force, which will create an overall net force upward of an attractive force towards this wire. Okay. So your only job then is to determine what this magnitude of force is. So not too bad. So let me stop sharing, and then we can break you guys up into some rooms and let you guys work on that. So we'll do 2 rooms. Okay. Create those, and we'll open those. Hello, I was just getting ready to come to you guys. So, what can I do for you?
We're truly just like, we don't know where to start.
Okay, so you want to use that equation that we wrote down. So basically, you want to say that the force between, say, the top wire and the first portion of the rectangle is going to be mu naught times I1 times I2 times the length, which the length in this case is going to be 20 centimeters, divided by 2 pi times the distance between the two, which in this case is 1 centimeter. Okay. So that is the force on the top portion of the rectangle. And that's an attractive force, so you know in that case it is pointing upward towards the wire, because the two currents are in the same direction.
So I have force equal to mu naught times current 1 times current 2. And then the length, was that
That's
A?
the length of the portion of wire of the rectangle, so that's 20 centimeters.
Okay.
Divided by 2 pi times the center to center distance between the wires, which is that A that you're told in the question, because those two are separated by distance of A, so that is 1 centimeter. Good. And that's an attractive force, which means that the force must be upward towards the wire. So call that, you know, the Y direction if you want to.
What is mu naught again?
4 times pi times 10 to the minus 7. So that's the force on the upper portion. Now the force on the lower portion is going to be the same thing. So it's going to be equal to mu naughts times I1 times I2 times the length, where the length in this case, again, is going to be 20, because it's 20 centimeters long, divided by 2 times pi times the distance between the two, where the distance between the two is now, well, you know, the side length is 8, but there's that extra 1 centimeter. Right, so the distance between the two then is going to be 9 centimeters. Is that okay? Now that is, the currents are running in opposite directions now, so that's going to be a repulsive force, so that one is going to be downward. So if you call y-axis positively upward, then that's going to be a negative force in that case. Then the net force is just going to be the sum of those two. So one is positive, one's negative, and now just add everything together.
You said the attractive force for the first one was they're going to, no, hold on. The top, that's with the top portion of the rectangle?
Correct. That's because the currents are in the same direction.
Yeah. So what do we do with that information that it's attractive, except that we know?
Well, you're saying that since it's attractive, call upward the positive y direction, so you know that force has to be in upward. So if you call upward the positive y direction, then it has to be in the positive y direction.
So I should draw an arrow from like for drawing the force on the diagram?
Yeah, so draw a force upward with that magnitude. Yes. That's right. And on the bottom portion, what's happening now is the two currents are in the opposite directions now, which means that's be a repulsive force, so that force must be pointing downward.
Not getting this answer.
Did I get my answer? I got a multiplied wrong.
No, I would not bet against you. Okay.
No. Well, never bet against my algebra, but definitely bet against my multiplication skills, because I can't always do that very well. So good. So now you have one force up and you have one force down. So make one of them positive and one of them negative. Right? So whatever direction you want to call positive. So if you call upward positive, then that means the top one is going to be positive, the bottom one's going to be negative. Or if you want downward to be negative or positive, then the bottom one's going to be positive and the upper one's going to be negative. Whatever coordinate system you decide to choose. And then those are the two forces which are acting on the wire. And now simply sum those two together with that negative sign. That might be off by a factor of something, but I'll check in a second, Adrian. But
I did it in centimeters, not meters.
well, that shouldn't matter because you have a length on top and you have a length on the bottom, so those two should cancel each other. So that shouldn't actually matter. Right, because you have mu naught I times L divided by 2 pi D, right? So if you use the same units for L and for D, which in this case is either A or A plus B, and if you use them both in centimeters, that shouldn't matter. Then the two units would go away. So what did you end up getting?
Me?
Yep.
I'm redoing everything,
Okay.
but for the top one,
Yep.
0.0036.
I never do them individually. I'm too lazy to do stuff like that, so I would do them both at the same time. So. I'll double check them. So, in the meantime, let me go check on the other group. I'll be right back. Okay. I'll check on that. All right, how are we doing, ladies?
I got the same answer as you, but my decimal place is 2 places over.
Yeah, I'm starting to think that might be true. I'm checking it now. So,
Okay.
so 20 times 1 over 1. Oops. What did I do? Don't argue with me. Okay, there we go. 1 minus 1 over 9, right? Oh, I forgot my 2 pi. So that should only be 2. What was the current again? 7.5?
They're two different.
There are 2 different.
ones.
Okay.
I want-
I'm thinking of the wrong problem. Okay.
Okay. I1 is 30 amps. I2 is 20 amps.
Right. Okay. I was thinking of the previous problem, so that's probably why it wasn't working. Okay. And the length is 30 centimeters, not 20 centimeters. And I remembered all the wrong numbers. Okay. I got the 1 and the 9 right, though. That's about the only thing. Okay. So, and I forgot my 10 to the minus 7. Man, today's going to be a long day. I can tell you that. Yeah, so it should be to the minus 3, not minus 5. Yeah.
Okay.
Yeah.
On the first try then. Yay!
Nice.
And when you were going through the example problem, you're like, got it? And I'm like, that was a lot of algebra that I barely followed. But I feel like I have a pretty good grasp on vectors. So it's like, if I can define it and be like, the force on the top minus the force on the bottom,
Yes.
then I can plug in the rest.
Yes. Yeah. I'm just lazy and I don't want to multiply things that I don't have to multiply multiple times. So to me, it's easier to spend a couple seconds doing it down to run it. What's that?
But I would prefer to do it the long way.
I'd rather spend a minute doing algebra to not spend an hour doing my calculator. So that's just me.
That's true.
Okay. Let me go check on the other group. I'll be right back. All right. So yeah, it should be 3.2 times 10 to the minus 3, not minus 5. So there's a typo.
Yeah, that's what we got.
Good. Cool. Sure, I've been telling myself for years now I'm going to fix that. I never fixed it, but it should be fine. Okay. So, everybody's doing okay?
Yeah, I think I'm just making some calculator errors, but I have this up, so
It happens, yeah. Yeah, unfortunately. Was that here you don't have to worry about putting the centimeters into meters because those units are going to cancel out anyway. So I might save you some calculator error. All right, well, if everybody has it, then I will break up the rooms and we'll start talking about solenoids. All righty, welcome back, everyone. So our next topic we're going to talk about is solenoids. So what's a solenoid? So a solenoid is a coil of wire which is carrying a current. So here is my solenoid. So basically this is a coil of wire which has some length to it. So most of the time we're going to pretend that this thing is infinite in length, but this thing has some length to it. And then this has a magnetic, it's going to carry a magnetic field due to the fact that it actually has currents running through it. And this thing is going to be the magnetic equivalent of a capacitor. And we'll kind of talk about why this is actually true. So what we want to do is start talking about what is the magnetic field of this guy. So to do this, let's imagine that I'm going to take this coil of wire and then cut down through the center of it. So I'm looking at the cross-sectional area of it. Okay, so let's say this is our cross-sectional area. So here I have the wire, so these guys are attached here, but I'm cutting it straight down through the center, and then we're going to look at it as the current is actually running through it. So let's say that for funsies, that down here, the currents are all running out of the page. So I have currents running all out at you down on this portion. And then we'll say up at the top portion, then we have the currents then going into the page, right? Because it's coming out, running back in, out, in, because it's doing a spiraling type pattern. Good. So first thing we want to start looking at is, well, what does the actual magnetic field look like? So what is the direction of this magnetic field? So first of all, when I'm looking at the cross-section here, these guys are constituting just straight wires, and we now know from right-hand rule number 1, we would then point our thumb in the direction of the current, and our fingers are going to curl around in the direction of the magnetic field, which means anywhere across this bottom portion, so when I'm looking at any one of these bottom ones, what that means then is we would put our thumb towards us, pointing in this direction, our fingers would then curl around in the direction of the magnetic field, which means that anywhere on these bottom ones, the magnetic field has to be running in the counterclockwise direction. So down here, my magnetic field is going like this, like this, like this, like this, like this, like this, and like this, right? Now on the top portion, we would then put again our thumb in the direction of the magnetic field, which in this case be going into, curl our fingers around in the direction of the magnetic field, which means that they would be going in the clockwise direction. So here, I would then have this magnetic field going this way, this one going this way, going this way, this way, this way, this way, and finally this way, okay? Now what? So now, let's start looking at what's actually happening here. So let me take an individual intermediate portion here and let's look at what the field is actually doing. So here what I can see is what? If I'm looking at this point, at this halfway point, what's happening is this portion of the magnetic field here is pointing upward. So this is going to be pointing up. So I have this portion of magnetic field here, but this one is running in the clockwise direction, which means that this same portion, this portion is actually pointing downward. Which means that the superposition of this field with this field at this halfway point between the two are going to be equal and opposite from each other since they're carrying exactly the same amount of current, which means this portion of the field actually cancels this portion of the field. Okay? The same thing is going to be true down here. Here what's happening is at this point again, magnetic field is running this way, so here it's going to be pointing upward. From this one, it's going to be running, oops, sorry, I went the wrong direction, didn't I? Sorry, one's going this way. Sorry. That one's going to be pointing downward. I was looking at it from the wrong angle. So this one is actually going to be pointing downward. There we go, B. This one is running this way, which means that this one is going to be pointing upward, which again means that this portion of the magnetic field will cancel this portion of the magnetic field. So anywhere that you are along this line, so along the solenoid, what that means is there's going to be no portion of the magnetic field which is actually perpendicular to the solenoid. Now let's look at what's happening in the middle. In the middle, what's happening is, again, and this one is running in this direction, so this magnetic field will point this way. This one is running in the same direction at that point, which means this magnetic field is also pointing in this direction, which means that anywhere along the center axis of this, all the magnetic fields were superimposed with each other to point along the axis of the solenoid. So basically, by looking at how all of these are superimposing on top of each other, all the perpendicular pieces will cancel, which means that only portion of the magnetic field will be along the axis of the solenoid itself. So this is going to be the direction of the magnetic field of the solenoid. Now, of course, the direction it's going to be going is going to be dependent on the direction the current is actually running. So here I have the current running out and then going in, which makes it point in this direction. If it was doing opposite, if it was running out here and coming in down here, it would point actually in the opposite direction. Okay. Now, turns out that this magnetic field is actually constant. So what happens is anywhere along the interior of this solenoid, the magnetic field is actually equal to a constant. And it's given by mu naught times little n times I, where little n is equal to capital N over L, which is equal to the number of loops per unit length. So little n here is basically the number density. So this is how many loops there are per unit length. Okay. So turns out that just like a parallel plate capacitor, so remember our parallel plate capacitor, so this was my parallel plate capacitor. What we saw with the parallel plate capacitor was that the electric field only pointed perpendicular to the plates themselves, pointed from one plate to the other plate, and we found that the electric field was actually equal to a constant, which was equal to sigma divided by epsilon naught, where sigma, again, was the charge per unit area times epsilon naught. Here, the solenoid works out to be basically the same thing. Now there is a magnetic field, which only points in one direction, whose magnitude is simply equal to a constant. That constant then only depends on the current, which is running through it, as well as the number density, which is how many loops there are per unit length. So this is what we call a solenoid. So solenoid, we'll talk more about solenoids actually in the next chapter and see why they're actually more equivalent of the capacitor, but we can kind of see that right now they're very similar in the capacitor in that the field is a constant and it only points in one particular direction. The solenoid is the same thing. So here, what's going to be true is that as long as this thing is infinite in length, the magnetic field of the solenoid on the exterior will be equal to 0, just like the electric field here was equal to 0 on the exterior. And the only place the field actually exists is in between or inside of the solenoid itself. So again, this only points along the axis of the solenoid, so along the axis of the coils, and has a constant value of mu naught times I. So this is what we call a solenoid. So let's use this and let's do an example. So let me get rid of some of these I don't need anymore. Down 2. So this says we have a solenoid which has 100 turns per centimeter, so that's our N value, and carries a current I. An electron moves within the solenoid in a circle of radius 2.3 centimeters perpendicular to the solenoidal axis. So it says the speed of the electron is 0.046 times the speed of light, and it wants us to find the current within the solenoid. So let's kind of draw what's happening. So what this is saying is that we have our solenoid. So here's my solenoid. We know this thing is carrying a current of I. And then what it's telling me is on the interior portion, let's say here, I want to do yellow. I don't want to do yellow. Let's do blue. Here I have an electron which has a velocity this way, and this thing is undergoing uniform circular motion, which means it's moving in a circle with some radius of r. Okay? And it tells me that v is equal to 0.046 times the speed of light. Okay? So this is kind of a side-ish view. So let's draw from the front. So if I draw a front view, here is the solenoid. Let's say for funsies, the current is going in this direction. Inside of here, we have our electron. So here's my electron, which is undergoing uniform circular motion on the inside of this with a radius of r. So from all of this, it wants me to determine what is the magnetic field, or in this case, more appropriately, what is the current which is running through the solenoid. So let's think about the electron. So here we know that the sum of the forces acting on the electron is then going to be equal to, since this is undergoing uniform circular motion, mv squared times r. Where again, v is equal to 0.046 times the speed of light. Now here, what we also know is that the magnetic field of the solenoid is perpendicular to the axis, right? So let's say this is the direction of our magnetic field of the solenoid. So what we have then is we have an electron which has a velocity v, so let's say our velocity is going in this direction, which is moving perpendicular then to the magnetic field, which means that what's keeping this thing in uniform circular motion is the magnetic force. So here we have the magnetic force, which is actually causing this thing to go under uniform circular motion. So remember, we're talking about magnetic forces. Whenever we have a charged particle moving perpendicular to a field, it has to undergo uniform circular motion. So here, what is causing this thing to undergo circular motion is the magnetic force. So we have the magnetic force then is equal to mv squared over r. All of my handwriting looks terrible today. Not that it ever looks good, but it looks worse today than usual. Okay, there we go. Now, what we know is that what? The magnetic force is equal to the charge, which in this case is going to be the charge of the electron, times the velocity, times the magnetic field, which in this case is going to be the magnetic field from the solenoid, times then sine of the angle between the two. But in this case, since the velocity is always perpendicular to the magnetic field, we know the angle is simply equal to 90 degrees, so this term is going to be equal to 1. So this says that we can write this as the charge of the electron times the velocity times the magnetic field from the solenoid is all equal then to mv squared divided by r. Now, since we know the magnetic field is from the solenoid, we now know that the magnetic field of the solenoid is equal to mu naught times little n times the current. So let's substitute that in. So this is going to become the charge times the velocity times mu naught times n times the current must then be equal to mv squared divided by r. Now this v is the same as this v, so we can go ahead and cancel this, and now we can use this to solve for the current. So this says the current then of the solenoid is going to be equal to the mass times the velocity divided by the charge times mu naught times n times the radius of our circle. Oops. Looking at our numbers, what we find is that the current works out to be 0.272 amps. So this is my current. So to get this electron to undergo uniform circular motion of a radius of, what was it, 2.3 centimeters? Yeah. Then I have to have a current of 0.272 amps. If I increase the current, what would happen then is that the radius would get smaller. If I decrease the current, the radius would get bigger. Okay. So that's it. That's the end of chapter 20. Exciting. So, having said that, we can now move on to chapter 21. So chapter 21 basically wants us to ask a question, and that question is, so far we've talked about electric fields, so far we've talked about magnetic fields, but are these two things related to each other? So the question is a magnetic field related to an electric field? So is this true? Now, if we did a simple experiment, like for example, we took a single charge, so let's say this was our charge Q, and this thing was non-moving, and then we put a compass needle near it, what would happen to the compass needle? Well, nothing. That compass needle would point in the direction of north. Let's say north still points in this direction. Life is great. But, so what this basically tells us then is that what? Here, this guy has a magnetic field. This guy has an electric field. And what this experiment would imply to us is that the magnetic field then does not talk to or interact with the magnetic field at all. So this would basically imply to us that E does not talk to B. But we also know, going back to what we just talked about last chapter, which is if I took a wire and I ran a current through the wire, say my current's going in this direction. Now, if I move my compass near the wire, what would happen in this case is, well, the compass needle would actually move, and in this case, it would now point in whatever direction. So in this case, we know the magnetic field is going to curl around this way. So let's say this is over top of it, so the magnetic field points this way, so north has now moved. So here, we can now see that there actually is a deflection. Okay? But we know this thing is creating a B field, and this one is creating a B field, so we know that B talks to B. However, what's a little bit weird about this is that even though this is a single charge which is not moving, this is actually multiple charges which are all moving, which means that we actually have moving electric fields. So even though what's happening here is I have these charged particles, little q's, moving in this direction with the velocity, the drift velocity, each one of these guys has their own electric field, which means that it is an electric field, but this is a moving electric field. So what this is basically trying to get us to kind of realize is that even though this is an electric field, this moving electric field somehow creates a magnetic field, which then somehow causes these two things to actually interact with each other. But this isn't the only way. So basically, what this kind of implies to us is that even though this experiment tells us that no, E and B shouldn't actually talk to each other and they shouldn't actually be related to each other, this actually tells us the opposite in the fact that, well, E, as long as it's moving, will then create and talk to a B. Okay? So the overall answer is actually yes, these guys are related. To each other. Now, our first question then is, well, how are these guys actually related to each other? And this is going to come from our observation here in the fact that, well, this thing was actually moving. Okay? So we want to understand how is this actually going to work. So we're going to look at actually the opposite. We're going to look at, instead of having an E field moving, we're going to look at what happens if I have a B field moving. So to do that, let me stop sharing, and then I'm actually going to look at, so let's look at this next beautiful experiment that I have sitting over here. This thing, I don't need you anymore. So hopefully all this shows up over here. So basically, what I have here is this big contraption. This is what's called a galvanometer. This basically measures current. Okay? Here I simply have a loop of wire. So this is basically a solenoid. So I have a loop of wire here, but inside of here there's no electronics. Basically there's no power sources or anything here. There's nothing that's going to create a current. Okay? So now if I take this wire and I slowly put it into the external magnetic field, which is this guy, and I let it sit there, you can see that there's no deflection of the galvanometer meter. So in this case, it means there's no currents running through here, so there is no power source. But now if I take this thing and I actually move it, my arm is not in the way. Is my arm in the way? I feel like my arm is in the way. Yeah. Oh, it broke. So now if I take this guy and I move him, you can actually see deflections of the compass needle, of the galvanometer here. So if I watch this guy, I move it, you can see it move in one direction, move in the other direction, which basically means that if this thing is moving, there has to be a current. So what this thing is saying is now if I take this magnetic field and I move this magnetic field relative to this loop of wire, or if I simply move the wire itself, I can actually create a current inside of this wire, even though there's nothing in here giving power. Or if I take this wire and I say squish it, or if I extend it, or again if I squish it, if I change the area, I can also cause the deflection needle to move. Or if I take it and I wobble it, can't see it as well, but if I sit here and I wobble it, I can actually cause that needle to deflect as well. So what this thing is actually saying is that if I somehow cause this magnetic field, or at least this scenario to change, I can actually create a current inside of this by the fact that I'm actually creating a power source inside of the wire itself. This power source is what we call an EMF, or more appropriately, what's called an induced EMF. So the question is, how does this actually happen? So we're going to talk about what we talked about in lab. First thing we're going to talk about is what's known as magnetic flux. Magnetic flux. So first of all, what is flux? So flux is the number of field lines which penetrate an area. I forgot to see if my kids had any bubbles, so that's all right. We'll look. So best way to kind of understand this is flux would be what? If I have, let's say if you want to blow bubbles from one of those, things that you put into the bubble solution, basically just soap water, you try to blow through it. So here, if you're trying to blow, so in this case, you have your mouth, you're trying to blow air velocity through into this direction. If I take that bubble thing and I turn it so that it's perpendicular, so this is the area, so my area vector then is pointing in this direction, you're not going to blow any bubbles, right? Because in this case, your flux, what we call flux, capital Phi, is equal to 0. There are no velocity field lines penetrating through this area. But if I still blow, so now I'm blowing again in this direction, so this is my velocity V, and I tilt, say this, so that my area now is, say, pointing in this direction. So now some of these velocity vector lines will actually start to pass through this area. You're now going to start creating a bubble. So now your bubble is going to start creating. So in this case, what's happening is now some of these lines are actually penetrating through this area. So now you have a non-zero flux until, if you keep rotating it, what'll happen then is what? So now if I keep blowing, so now I still have my velocity vectors going in this direction, but now I'm going to take my area and tilt it. So it is at 90 degrees relative to the velocity, or the area vector points parallel to the velocity vector. So this is now my area vector. I'm now going to be able to create the bubbles the easiest. So now here's my bubble because it has the greatest amount of flux. So this is what we call volume flux. So volume flux says that this is equal to the velocity dotted by the area, which is the same thing as the velocity times area times then cosine of the angle between the two. Magnetic flux is basically the same thing. So I have, instead of velocity vectors from the air that I'm blowing going, instead, I now have magnetic field. We then define the magnetic flux, phi of B, as then being the magnetic field dotted with the area, which is then the same thing as the magnetic field times the area times cosine of the angle between the two. So here, what this means is that we have magnetic field pointing in some direction. So this is my magnetic field. We have some area here. So let me draw that in blue. So here is my area, where again, we classify an area by a vector which points perpendicular to the surface of that area. So in this case, this would be my area vector, A. Then the angle then, theta, is the angle which points or between the area vector and the magnetic field. So this is theta then. So what this says is that flux, which is the magnetic flux, is then equal to, again, the number of magnetic field lines which pass through that area. So what this thing is saying is that what? That depends on the angle. So again, if I have that the area vector is perpendicular to the magnetic field, or the face of the area is parallel with the magnetic field, no flux lines pass through it, so it's going to give you 0. As I slowly rotate it, it's going to gain the most amount of flux when these two things are parallel to each other. So when the face is perpendicular to the magnetic field, or when the area vector is parallel then to the magnetic field. So this is what we call magnetic flux. Just different from the volume flux, because volume flux has to do with volume flow rates, so how fast fluids are flowing. This has to do with magnetic fields itself. So this is what we call magnetic flux. So how does that relate to our EMF? So how we're generating this guy. So let's look at a couple different scenarios. So the first scenario we're going to look at is, let's say, here's our loop of wire. So here's our loop of wire. And let's say we have a magnet. Here is our magnet, which is N, S. So here's my magnet, which then has a magnetic field pointing down in this direction. So this is B. So we know that's what B actually curls around. It's going to create closed loops. So here's my B field. And let's say what happens. So now let's take that and let's say we'll move it in this direction with a velocity of V. Okay. So what's happening is, as time goes on, so I have a time change going from here to here, so I have a delta t. I have that same loop, but now my magnet is going to get closer. So now my magnet is going to be closer, still moving downward in this direction, my velocity v, but what's happened now? So initially, let me draw a couple more field lines on here. So here's another field line, another field line. Let's draw those same field lines here. So there's that field line, that field line, this field line, and this field line. So basically what's happening is the difference between this scenario here and this scenario here was initially there might be, say, 2 magnetic field lines which are passing through this area, which has a cross-sectional area of A, as opposed to here, at some later time, it now has 4 field lines which are actually passing through. So initially I have this field line and this field line, so I have 2 field lines, but now I have this field line, this one, and this one, so now I have 4 field lines which are passing through. So what has happened is, even though the magnetic field strength is the same, because the magnetic field is only dictated by the fact that this thing is a bar magnet has a solid magnetic field, but what has changed is the number of field lines which are passing through this area, which means the flux has changed. The magnetic flux now has increased going from this time to this time. Now, at the same time, if we did the opposite, if I pulled it away, meaning if I went back in this direction, if this was my delta t, so that my velocity was actually in the opposite direction, so if I was moving it away, it would just be the opposite is true. So initially I would start off with 4 field lines. I would then reduce down to 2 field lines in a time frame of delta t, which means that, again, I would have a time-changing electric flux. So what Faraday's law says is that to have a current being induced inside of this loop, well, what we know from Ohm's law says that the change of potential must be equal to the current times the resistance. So if this loop has a resistance of R, and we're measuring some sort of current, which initially was moving in this direction, when it's moving with the red, and with the yellow, the current would actually be going in the opposite direction. We'll talk about that in a second. What this means is, by Ohm's law, to have a current moving, we have to have a potential. So what Faraday's law says is that this presence of the current is due to the fact that we have some sort of potential which is being created inside of the wire, which means that this potential, or this EMF source, is then equal to the change of the potential divided by the change in time. Because again, it's not just the fact that we have a flux, because again, if I simply put this coil inside of this external magnetic field and let it sit there, it has a flux, but that flux is not changing with time. The only way to get this thing to actually induce something is if I move it around and I change this flux as I change time. Okay? So what Faraday's law says is that, well, to get a current to move by Ohm's law, I have to have a potential. So what's really happening is I'm creating a potential, or an EMF, inside of this coil, where this magnitude of this EMF then is equal to the rate at which this flux is changing. So this is Faraday's law. So this says that the induced EMF is equal to the rate at which the magnetic flux is changing. Okay. Now, before we move on, this can happen one of three ways. So what are the three ways this can happen? I like carrying lines, these things. Okay. Anyways, way number one. My EMF then is equal to the time rate of change of the magnetic field times the area times cosine of the angle between the two. Okay. So this means that, let's say I had a coil of wire and I put a magnetic field inside of it. So let's say I have a magnetic field, say, pointing in this direction, and I change the strength of the magnetic field over time. Okay. So basically, this magnetic field is time dependent. So I'm going to increase or decrease the strength of the magnetic field. This is the first way this can happen. Number two. Number two is I can change the area with respect to time. So this is going to be the magnetic field times the rate of change of the area times cosine of the angle between the two. Okay. So this one can happen by, let's say initially here is my coil, which has a cross-sectional area A, and again I have a magnetic field, let's say B, but B here is going to be equal to a constant. So in this case, this is what happens when I squished that wire, and let's say what I did is I decreased the size of the wire. So now I have gone from this area here down to this area here, which has now changed the flux. So in this case, my area is actually time dependent. Okay. So this is the second way it can happen. The third way this can happen is if the angle is actually time dependent. For example, the angle could be equal to omega times t. So in this case, what we can do is we can take a coil of wire with a cross-sectional area A, and we can rotate this about its axis at an angular velocity of omega. Okay? So this thing is actually rotating in an external magnetic field. Okay. So, I almost out of time. Okay, so this is the third way that this can happen. In this case, my EMF then would then be equal to the magnetic field times the area times the angular velocity times cosine of, times sine, there we go, of the angular velocity times the time. Okay. So these are the three ways that this can actually happen. Okay. So Faraday's law basically goes on further to say that the EMF is actually equal to minus, we'll talk about that minus sign, N, where N is the number of coils, times the change in flux, magnetic flux with respect to time. So N here is equal to the number of coils. So this is N. One second. Sorry, thought I heard something. Okay, so this just means that what if I have a bunch of coils of wires basically all on top of each other, then if each one of these coils has an induced EMF of the change in flux with respect to time, then each one of these coils will have exactly the same, which means I'll just add them all together, which is where that factor then comes from. Okay. Now let's talk about that negative sign. This negative sign has its own law, which is known as Lenz's law. So Lenz's law is the interpretation of this negative sign. What Lenz's law says is that the direction of the induced EMF, i.e. the induced current, happens to oppose the change. So this direction of the induced EMF is in the direction opposite to the change. So basically, what does that mean? So that means is that it wants to maintain status quo. Status quo. So basically what it wants to do is it wants to maintain the fact that what? The overall magnetic field is equal to a constant. So for example, if we go back to our wire here. So here, if this is my wire with my magnets, so this is the north side and the south side. And let's say, again, this thing is moving in this direction with a velocity v, so that its magnetic field is also pointing in this direction. What it wants to do then is create its own magnetic field, which is in the opposite direction of this external magnetic field, so that the sum of the two magnetic fields together will remain a constant magnetic field. Okay, so what does that mean? So that means that as this magnetic field here is increasing, so this magnetic field is getting stronger since the velocity is in the same direction, this guy now wants to make his own magnetic field. He wants to induce his own magnetic field be induced, which is in the opposite direction as the external magnetic field, which is then going to cancel the change. Okay, so he wants to be that the sum of this guy with this guy is equal to the original magnetic field. Okay. Now, to do that, we use our right-hand rule. So in this case, it would be right-hand rule number 3, where we curl our fingers around in the direction of the current. Our thumb then points in the direction of the magnetic field. So in this case, our induced magnetic field would be in the direction of this, because again, by right-hand rule number 3, we'd curl our fingers around in the direction of the current. Our thumb would then point in the direction of the induced magnetic field. In the opposite case, where if this was my loop of wire, we have that same magnet, and with S, B still now points in the same direction. But now if we switch the direction of the velocity, so now we move it away from the coil, what's happening in this case then is that this magnetic field is decreasing with time. So since this one is decreasing with time, this then wants to induce its own magnetic field in the same direction. So this can be the direction of be induced, which means we'd curl our fingers in the opposite direction to have our thumb point downward, which means that the current in this case would have to be in this direction. Okay. So this is the interpretation of that negative sign. So the negative sign gets its own law called Lenz's law, which is that the direction, again, of the induced EMF or the induced current is in the direction which opposes the change. Okay. So this is that negative sign. So if you want to think about the negative sign, just think about that as your friend that tried to keep you from doing stupid things when you're drunk. That's what this negative sign is. Right? So when you get out and you get drunk and you think it's a great idea to climb up somebody's balcony to go in through their balcony window and they say, you might not want to do that. That's this person. Okay? So it's the person that tried to keep you sane and level, the same all the time. Okay? Now, this is going to be opposite to when we talk about the other direction, which is going to be a positive sign, but we'll talk about that when we actually get there. Okay? So this is Faraday's law. So Faraday's law says that as long as we have a time-changing magnetic flux, That magnetic flux then has to induce an EMF, i.e. a power source. That power source then simultaneously induces a current as long as I have a resistance. And then that current induces a magnetic field where that magnetic field is in the opposite direction of the change. So here we have to pay attention to now multiple things. We have to know the direction of the external magnetic field, and we have to know, is it increasing or decreasing? So knowing only the direction of the magnetic field isn't enough. We need to know, is that guy increasing? Because if it's increasing, the induced magnetic field is in the opposite direction, as opposed to if it is decreasing, the induced magnetic field is in the same direction. So to fully do Lenz's law for Faraday's law, we then have to know the direction of the external magnetic field and is it increasing or decreasing. So there are many different things we have to pay attention to. But again, Faraday's law says if this thing is changing, that induces an EMF. That EMF induces a current. That current induces a magnetic field. But we get the direction of the EMF and the direction of the current based off the direction of that induced magnetic field. So this is Faraday's law. So we're out of time. So tomorrow we'll do some examples of Faraday's law. Okay, so we'll start off with examples of that and talk about some other things and pretty much go from there. Okay. So Faraday's law takes a little bit to kind of get used to, but once you get used to it, it's not too bad. Hopefully. It should be fun. So any questions at this stage? Are we doing okay? Not too bad. Okay. One thing I will point out before I let you go, Faraday's law is always one of the long questions on the upcoming exam. Okay, so we'll see how to do those tomorrow. So expect one of those to be a long question on the exam. All right. So, are we doing okay? Far so good? Okay, so have a good night. I'll see everybody tomorrow. Remember, no lab tomorrow, so just class tomorrow. So it should be great. All right.